bigger embeddings are not always worth the cost. Matryoshka Embeddings let you shrink vector dimensions and measure how much recall you actually lose. This is the setup you'll be able to run after this, which tests nested embedding sizes, measures recall on top results, and chooses the smallest dimension that preserves retrieval quality. I'm Professor Pi, teaching search and IR with simple Python. Search systems often use large, dense vectors to represent text. Bigger vectors can capture more nuance, but they also use more memory and slow down nearest neighbor searches. Matryoshka embeddings give you a way to make smaller versions of those vectors, like nesting dolls. You create a full vector and then trim it to smaller sizes. Then you check whether the trimmed vectors still return the same top results you care about. Success looks like keeping almost the same top hits while using less space and faster queries. The intuitive idea is simple. Encode documents with a sentence embedding model to get full vectors. Then drop trailing dimensions to form smaller vectors. Renormalize so cosine similarity stays meaningful. Compare the top results between full and trimmed vectors. If most queries return the same top matches, the smaller size is a practical win. The cost is that some fine distinctions vanish when you shave away features. The trick is to measure that loss quickly and pick the smallest size that still works for your use case. We will build a tiny, readable demo. It embeds a short corpus, creates truncated variants, tests ranking overlap, and time searches. You will see how quality and space change as dimension drops. This keeps the code friendly and the metrics actionable. Now we will load a tiny model and embed a short corpus. This snippet loads a SentenceTransformer model and encodes a tiny, readable corpus to establish a working baseline. The variable docs contains short energy-related text to keep semantics interpretable. The object model is a SentenceTransformer loaded from nomic-ai, nomic embed text v1.5, which produces embeddings suitable for Matryoshka truncation. The call model.encode returns L2 normalized vectors when normalize embeddings is true, making cosine comparisons equivalent to dot products. The array X holds the dense representations, and mem_mb estimates storage using the array's n bytes. Increasing corpus size, or dimensionality, grows mem_mb linearly. The printed shape and memory quantify the starting cost before any truncation. This gives a clear, measurable starting point, so each later truncation has a concrete baseline to compare against. Next, we will create a truncation function and run a short comparison. This example applies a Matryoshka-style truncation by taking only the first d dimensions and renormalizing. The function trunc crops any vector or matrix to d features and performs L2 normalization to keep cosine scores consistent. The variable q stores a single query, and model.encode produces its vector qv comparable to the corpus X. We compute sfull as dot products for full dimension retrieval and str for the 256-dimensional variant. The array's top 3 full and top 3 tr hold the highest scoring document indices under each setting. The overlap score indicates stability of the top results under truncation. Lower d generally reduces agreement but improves cost. If you increase d, you should see overlap rise, and if you drop d, you trade recall for savings. Now, we will probe multiple queries to get a small stability estimate. This snippet evaluates a small query set to estimate ranking stability at k equals 10. The list QS holds 3 varied queries to probe different semantics. For each query, model.encode creates a normalized vector v. Then IDSF stores top 10 indices from full embeddings X, while IDST stores top 10 from the truncated and renormalized XT using trunc. The variable pairs zips these two rankings, and OV averages the set overlap ratio across queries. This gives a quick, label-free proxy for recall change relative to full dimension. Increasing K usually raises overlap, whereas decreasing D tends to lower it. The printed mean overlap summarizes how much ranking signal is preserved, which you can use as a guide to acceptable quality loss for your application. Next, we will build two flat indexes and measure timing differences. This snippet builds two FAISS index flat IP indexes to time and searches with SentenceTransformer's embeddings. The index F uses full dimension X, while index T uses the truncated and renormalized XT. The matrix QF stacks multiple encoded queries from QS, and QT is obtained by applying trunc to QF, keeping normalization consistent for inner product search. The calls index.search return nearest neighbors. We only use them to time per query milliseconds via time.perf counter. Reducing D directly shrinks vector memory and often lowers FAISS latency due to cheaper arithmetic and better cache behavior. The printed latencies show the runtime advantage gained from truncation, and you can expect larger speed benefits as corpus size and query volume grow. Now we will compute a final compact baseline and report trade-offs. This snippet finalizes a compact baseline by reporting quality and space savings for a chosen Matryoshka dimension. The value D is the original dimensionality of X, while D is the truncated size used to form XT. For each query in QS, the code computes top 10 sets from the full vectors and from the truncated vectors, and averages their overlap into qual. The variable space quantifies the storage reduction relative to D. If you increase D, expect higher qual but lower space saved. Reducing D trades recall for memory and speed. The printed line presents a concise, decision-ready trade-off for a practical baseline. Use that line to pick a dimension that balances your latency and memory goals against acceptable ranking change. In a production setting, you would run this with a larger corpus and more queries, then store the chosen small vectors in your ANN index. The same trade-off applies. Test K you care about, pick D that keeps overlap high enough, and enjoy faster queries and lower storage. Recap: Matryoshka embeddings are nested truncations of full embeddings used to trade recall for space and speed. Use them when memory or latency matter, and you can tolerate small ranking changes. Caveat: very low dimensions can break subtle semantic distinctions and hurt downstream tasks. Next step: tune the truncated dimension D across a wider grid, while timing FAISS and tracking top K overlap to find the sweet spot for your dataset. If short, practical IR helps, subscribe and watch the IR videos.